Good evening, my audience. Today our radiology talk will be about the MRI signal to noise ratio, SNR, and image details. As we all know that this subject, the image details, is very crucial and important for every MRI practitioner. It reflects and can assess the efficacy of MRI machines, efficacy of MRI protocols, and planned sequences. We start, as always we do, with definitions, including first the noise and the image matrix, which includes the pixel and voxel definitions. Let's start with our major topic, which is noise, MRI noise. And when we talk about noise, first we have to demonstrate this diagram, which clearly visualize the effect of blaring and noise on the image detail. Let's start by talking about this diagram. The vertical direction of this diagram includes the object contrast, and it starts from high to low levels. And the transverse direction reflects the object size and also starts from large object size to small object size. The image of MRI, when talking about details, is composed of two major elements. The first element is the intensity of the object, and the second element is the anatomical details, size, margin, boundary of the object. But if we start with the bottom of the transverse and vertical dimension of this diagram, we are having large objects with high density, which is the most and betterly visualized object in the MRI signal. If we go towards reducing intensity of the objects, once we are not seeing low intensity objects, we are approaching the noise effect in the MRI image. And at the same time, if we go from large to smaller objects in the MRI image, and when we approach a level that we couldn't identify anatomical boundary of a very small object, we are going towards blare of the MRI image. And this zone is the invisible or poorly visible zone, and this zone is the clearly visible zone on the MRI image. Let's now make our definition of the MRI noise. MRI noise is the variation of image detail that comes from interference of RF signal due to random RF image. This is the definition of noise. And how it appears, as we see in the clearly visualized image in front of us, it appears as irregular, grainy, non-uniform like appearance of the MRI image. Compare it to the clearly defined, homogeneous, uniform image of the MRI, and looks how grainy this left-sided image. Of course, we have to consider that this is the original perfect image, and this is a high noise background image. We can raise the question about the source of noise. The answer is this random RF energy can be generated by thermal activity within the electrical conductors and circuit components of the receiving system. And by the way, the patient body is the largest RF receiving system, and so is the largest source of noise in MRI image. Other devices in the environment includes coils, data cables, fluorescent lights, and computing equipment contribute to this random RF energy emitted power, which interfere with the MRI signal. And how we quantitate the noise in the MRI image, this is by measuring the SNR ratio, signal to noise ratio. And we have to say that increasing signal to noise ratio means improving image quality, and decreasing signal to noise ratio means decreasing signal and image quality as compared in clearly defined in these two images. This is the perfect SNR ratio. This is the low SNR ratio, which reflects increasing noise compared to the signal. Let's continue. And the second definition that we need to know is the image matrix. Image matrix is a well-known term for every MRI practitioner, and it reflects a two-dimensional array of elements arranged in columns and rows. And this individual element in the image matrix is called the pixel or picture element, which reflects the signal coming from the body as a source. And in two-dimensional, we call this reflection of signal a pixel, and it is in reality corresponds to a three-dimensional volume element in the object itself, which is called the voxel. We'll see it clearly in the next image. This is, suppose, the image matrix, and this is the voxel, which is the three-dimensional component volume representing element of the body or object, and the two-dimensional part of this is called the pixel, which contains the picture element and MRI image. The field of view, let's go back to the previous signal, is the diameter of the body that is being imaged. Okay? These are the major definitions that we need to know when talking about noise in the MRI image. By conclusion, early for this method, we come to say, according to these informations, the fact that is MRI image is not created by pure MRI signal is completely true. It is rather a form of combination of MRI signal and unavoidable background of noise. So we can say that MRI image is a signal plus noise. If we want to improve the image, we have to strengthen the signal and reducing the noise because the noise is always present to a variable degree in every MRI image. This leads us to a question: is noise an artifact or not? By definition, noise is most likely is not an artifact. Why? It is always present, it is rhythmic, it is continuous, but artifacts are usually irregular, irrhythmic, and partial, and not always present. Now we come to the second part of the lecture, which is the factors affecting signal to noise ratio, SNR. We'll start by the first factor, which is non-operator dependent. It is the MRI field strength. MRI field strength, if it increases, it will enhance the SNR signal and subsequently improve the image. And also, we have not to forget that high strength MRI fields will generate high spatial resolution and also less scan time. The second factor that affects the SNR is the radio frequency coil, and we are talking about radio frequency coil. We are talking about transmitters and receiver coils that directly affect the SNR. Remember the two facts when talking about radio frequency coils that will affect noise. One is how close contact the coil, I mean the receiver coil, to the body will give us a higher SNR and better image quality. This is point one. Point two is increased number of elements in the RF coil will increase SNR and produces high quality image. And of course you see in the image how 16 channel difference from 2 channel receiver coil. The third factor that affects signal to noise ratio is increasing the TR. Increasing the TR will enhance the SNR and subsequently will enhance and improve the image quality. How it works? Increasing TR always producing or allows the longitudinal magnetization to approach its maximum and generate a higher signal. Higher signal means higher SNR and subsequently improving image quality. But keep in mind, please, that this subject is up to limit, because increasing TR over certain numbers will decrease the T1 effect. So we will reduce the valuability of the MRI image. The other factor is the TE and SNR. We remember that increasing the TE will reduce the SNR. Why? Because while we are increasing the TE, we are forcing the transverse magnetization for longer decay and more loss of signal and weakness of signal. And of course, if we decrease the TE, this will enhance the signal noise ratio and makes the image better in quality. But remember that if we extremely reduce the TE, then this will affect the T2F signal and affect the sequence and the interpretation of the image. The flip angle, also a parameter that affects the SNR. The statement is increasing the flip angle increase SNR ratio. How? It works by increasing number of exciting protons and increasing signal. But also remember that this subject is up to limit. Further increase in the flip angle will affect the quality of the image reversal. The other factor is slice thickness. Of course, increasing the slice thickness, it means increasing the signal to noise ratio. Why? Because of increasing voxel size. Voxel size, when increase, it produces more signal received by the individual voxel and subjectively more pixel visualization of signal and improving the SNR and image quality. If we go to the matrix per se, matrix has a reverse relationship with the SNR. Increasing the matrix size will reduce the SNR because of reducing the size of voxel and reducing the signal received by the pixel. Field of view and SNR. Increasing the field of view leads to increased SNR. Why? Because of increasing pixel size and amplifying the signal captured by individual pixels. The bandwidth Every operator in MRI knows how increasing the bandwidth will reduce the time of examination, but in relation to the signal-noise ratio, increasing the bandwidth will reduce the SNR, and decreasing the bandwidth will enhance the SNR and enhance the image quality. To say definition for the bandwidth for the beginners and who is interested in definitions, the Sakher bandwidth refers to the range of frequencies collected during the reception phase, which is the frequency encoding. This is the range of frequencies used. Next, and SNR, next means the number of excitations. Number of excitation is, of course, a measurement parameter used to represent how many times data is acquired to form the same image, and the relation is increasing the number of excitations always improves the SNR and improves the image quality, as we see in this example. There is also slice gapping that affect SNR. How? The slice gap is the distance between two slices, adjacent slices of course, usually calculated by a formula which is the slice gap equals half of the slice thickness. Increasing slice gap, decreasing the overlapping and improving subsequently the SNR, but also up to limit. We notice when we talk about these factors that up to limit is a very frequent word and limitation for the use of these parameters to adjust or improve the SNR. And we have to remember another important point, that sometimes improving the SNR will reduce the blurring and image detail regarding the object anatomical definition and boundary. And always, as an MRI operator, please remember that the time of acquisition is very important to adjust when dealing or making your protocol and parameters to achieve a high standard SNR. Usually SNR optimal is 100%. Below that, it is starting to reduce the quality of the image. And by this we come to our conclusion, which we will put the factors affecting SNR directly, and we'll name it quickly: MRI field strength, radio frequency coil, TR and TE, flip angle, slice thickness and slice gap, matrix size, field of view, receiver bandwidth, and number of excitation. Thank you for listening, and hopeful to see you again in another important and useful radiology talk.